Guys, and in this section, I would like to take the time to explain to you about how neural network works and why it works. So when we get started with the code, you'll understand how to train or at least why all of this happens and how it happens. So it's very fascinating. So try to draw a model for you to show you everything in an easier way so you can understand it better. Let's get started. So I am using my computer for these models, and I don't have like an iPad with a pen, so I'm trying my best to draw these models. Just know that they won't be the best, right? So, what is a neural network? Well, a neural network is a connected layer of neurons. What do I mean by that? So, when we say neural network, right? So, the word, it has neural and it has network, right? So, a network is like a group of something, right? And neural relates to the word neuron, right? It's the verb of it, right? So when we're looking at the brain, right? Something that just popped in my head when I was getting started with this, right? Neural, I thought of neurons. And if that happened to you, you'd be exactly correct. Neural networks is modeled after the brain. So that's why I think it's really fascinating because it takes math, it takes biology modeled after the brain, and it takes programming. It combines all of those to create neural networks, right? So when we think of the brain, we think of neurons, right? Neurons connected to perform a certain task, right? And in the brain, all the neurons are connected in some way, right? One neuron has to be connected to another neuron, right? So we have these neurons. There are millions of neurons in your brain, and fun fact, there are thousands of them in other organs, such as the heart. Let's not get too deep into that. So, for example, this neuron could be connected to this one, and this could be connected to this one. This could be connected to this one, and maybe this could even be connected to this one, right? So you can see how they're all connected in some way, right? So now, the more connections these neurons have, the more complex the structure is, right? So the more connections you have in your brain, the more you can do, right? So a really smart, genius person, if we take the example of Albert Einstein, would have lots of these connections, right? So if you can take the time to learn one new thing every day, your neurons will get more connected, right? So now, these neurons, we can say, is either they're either fired up or they're not. So let's say you touch your keyboard, right? Now, what might happen is these neurons might be fired up, right? This neuron may be fired up, right? And because this guy, here, let me draw this a bit better. This neuron will be fired up, right? So because this guy has a connection to this guy, right? This neuron fires up, maybe. Let's say. So now, why does it fire up? Because maybe like you touch it and it's like, oh, I remember something, or I remember this. You have to type F5 to open a new tab, something like that, right? So all these things are fired up. Thousands of millions of neurons are getting fired up. Thousands of millions, right? So let's say, right, we only have five and six actually in this diagram, but many of them are firing up because maybe they know this or they have a memory of this, something like that. So same thing in neural networks. So as I said before, a neural network is a connected layer of neurons, right? And this is exactly what we're seeing here, right? So this big structure, or this structure, is basically just connected neurons, right? The brain is basically just connected neurons at its core, right? I mean, there's obviously many things that the brain does, but at its core, it's just layers of connected neurons. All right, so that's that, and let's see how this relates to neural networks, right? So let's erase all this. So now we have in neural networks, the first layer, right? We have layers, right? And the first layer is what we call the input layer. So let's draw the input layer right here. Now, this is all the data that you want to feed to your neural network, all right? And all this data, or all these circles, right? These are what we call neurons in neural network, right? So what is a neuron in neural network? But this is a mathematical function. So each one of these are mathematical functions, or you can think of them for now like a value, right? So we can maybe say that this one has a value of 1, this one has a value of 0, right? Or something like that. So let's draw 0, right? And then so on and so forth, right? So this maybe have a value of 1, same with this, and then maybe this has 1 too, and then this has 0, right? So each of these, they have a value, which you can see right here, and each one is a mathematical function. So as I said earlier, neural networks is basically math, biology, and coding combined, and that's why I think it's so fascinating. Well, here's what you have. So in this video, we're going to be working with TensorFlow, right, to help us. And what TensorFlow is basically doing is it's covering the math, because this is very complex math, right? This can get into calculus. At the bare core, it is high school level, and I mean, most of you guys watching this video may know this, or not most of you. Some of you guys watching this video may know this math. But it's a lot. It's a lot. So to make it simple for us, we can just use TensorFlow, which is a module in Python that allows us to code without having to worry about the math per se. So this is what we call our input layer. So this is all the data we're going to feature. Right? So right now we have a bunch of 1s and 0s. Okay. And next, we can have what we call hidden input layers. So these could be hidden input layers between our input layer and what we call our output layer. All right, so we can put this in a slight, I guess you can call it pink color. All right, so this is what we're going to call our output layer. This is what the set of rules that we have defined. All right, so you can think of these layers as these are input layers, except they're just they're hidden input. So these are the layers in between. So you'll have many of these. You don't even have to have one. But these are most highly trained models, or really good models, will have these hidden input layers. Just more data. So basically, this output layer should have your output. All right, so in neural networks, we have some input and our defined input. To train a model, you give the defined input, right? Or the actual input, right? So let's say we have pictures of cats, all right? So we have pictures of cats. Okay, so let's get some pictures of cats here. All right, so we give it actual cats. All right, so let's say we give it this data, this image, and this image, or thousands of images of cats, right? And maybe the main ones would be in our actual input. So let's get back into our panes. So maybe these would be our actual input, and these will all be the hidden, the extra counts. So now what the model is trying to do is it's looking at all this info, and it's finding similarities, or it's finding a set of rules that they can define. So the computer has a set of rules that it's defined for a cat. All we're doing, we're giving it inputs and saying this is cat, or this is a cat. And now the neural network, it's trying to say, all right, what is actually a cat? What can I have? What are the features in a cat that allow me to define cat, right? So then later, when we give it data that we don't know, if we give it a picture of a dog and a cat, the neural network has to figure out, does it have these similarities? And if it does, it's a cat, right? And the more data we get, the more similarities we can find. So later, so this is our expected output. These are the pictures of the cat, and we're telling it that this is a cat. Then it finds out maybe some features. Now, what are these features? Well, these features could be things like maybe claws. Cats have claws. Maybe a specific type of fur. Maybe a specific type of canines, teeth. All these different similarities, right? And it finds an output. So this would be the output. This could be like claws, teeth, canines, all these things, fur, everything that it's found based on the data is in in the output, right? So now maybe we can have this program which you give it some pictures and it has to figure out if it's a cat or if it's a dog or any animal, right? If you give it a horse, it has to look. Does it have this specific type of canine? Does it have this type of fur? Is it this tall, approximately, right? So that's essentially how a neural network is trained and how it works, right? And now, as we said earlier, many times a neural network is a connected layer of neurons, right? Though in this model, there's something wrong about it. There is no neurons that are connected, right? So, I mean, obviously these ones should be connected because it's all in the same model. I tried to draw that with the circle, but how does this data go past through this, right? So this is not a neural network. This model is not a correct diagram of a neural network. So we need connections. And in your brain, if we look back, in different parts of your brain, you have different connections, right? Not all neurons are connected to each other, right? Maybe memory neurons, or I don't know the specific term, but we could say memory, the neurons that work in memory, right, or for memory, they might not connect to one in smell, right? I mean, they probably do some, right? Memory of smell, but well, let's say they don't, like one doesn't, right? So that changes the whole aspect. That changes the whole model, the whole how it works, right? How the brain works. So we have different types of connections for different parts in the brain, right? So same with a neural network, we have different types of connections for different neural networks. Right. So famous connection for a neural network is what we call a fully connected neural network, right? By the way, if you don't memorize all these terms, you guys don't have to. I would recommend if you guys take notes, but I do already have all these notes for this tutorial very briefly, but with all the names in the description. So if you guys maybe forgot of a name, you can just check out the 1 or 2 pages per each video in this course, so you can help. So anyways, a fully connected neural network is probably what you think. It means all the neurons are connected. So what that means is from this layer to this layer, all the neurons are connected. So we can draw it by just connecting all these neurons to this one, and then like this, and then all to this one, right? And then I don't want to draw the whole thing out because it's just going to mess it all up, right? It's just going to be way too much, and you guys won't understand. But let's just try to do as much as we can. As you can see here. See how all the neurons are connected. So this is what we call a fully connected neural network. So yeah, all of them are connected. I think you can get the terminology. All right, so now we got all right. So let me erase some of these so we can focus on one first. So all right, so each of these connections we call weights. All right, so weights. It's kind of all right. Can I draw this good? All right, so we call weights. So each of these connections we call weights. So this could be weight 1. This could be weight 2. Right? I'm not gonna draw all of them out because it's kind of hard. But anyways, just keep that in mind. And we're probably gonna cover it later in the other videos. All right, so now let's talk about what we call activation functions. Right? As I said earlier, in the brain, the more connections you have, the more complex the brain is, or maybe in slang terms, you could say the more smarter you are, right? And activation functions allow you to have more connections and make your neural network more complex. Okay, so let's take out all these connections just for simplicity. We talk about what an activation function actually is. Right, so let's start off with an example. Right, so I just told you an activation function allows you to make your neural networks more complex. But so now let's talk about some things in activation functions. Right? So what properties, or maybe why do they make it more complex? So an example of an activation function is what we call the TON activation function. That's just one, right? There's many. There's a lot, and this isn't like the most famous one. This is just one that I just picked up because it's kind of simple to explain and draw out. So basically what this TON activation function allows you to do is it allows you to map any value given in between -1 and 1. So before this, we've been talking about what we call linear regression functions. All right, let's break this term. So linear means line. Regression means like stats, things like that. So it's data graphs linear. Well, that's not a good explanation. But anyways, we just think about this is a linear function is drawn like this, right? This isn't the most important part of the explaining, but like just stick around so you can like just see this. Maybe draw the diagram because it will come useful later, right? So this is what we've been doing, and we call this linear regression, right? So this only allows us to have this straight line, and you can think of this straight line as like the lowest complexity. We can only go up. That's all we can do. We're only going up in the straight line, and it's just linear. We can't have any curves, and you can think of this as the core of complexity, right? Not core, but the least complexity you can have is just a linear regression function in your networks. So what activation functions allow us to do is they allow us to have more curve-like structures you can think of. So the TON activation function would look something like, here, how can I draw this in curves? Would look like this, right? So we can, what is this? All right. Anyways, it'd have like not like that. It would be more I'm just gonna draw it in line. But just notice that all of these aren't straight lines. I just have to draw it like this in the diagram because it's not allowing me to do anything. It's not allowing me to give me the curves and things. So it'll be like something like this, where we can have all these curves. And you need to understand that all these curves are not straight lines. So I'm just trying to draw this diagram the best I can. But please do not take it that these are straight lines. These are all actually curves and things. I can only just draw straight lines here. So this would be 1 here, and then down here would be -1. So this allows us to graph anything from 1 to -1. So this does is you can use more curves, or in this sense, more complexity. And this activation function, what this is doing is it's graphing it either closer to -infinity or closer to positive infinity. And for example, 1 is closer to infinity because it's positive, and -1 is closer to -infinity because it's negative. Right. So let me just pull you a picture of actual ton activation function diagram. So if you look at these images, you can see it's kind of like this curve-like structure. -1. So you can see that. And I mean, I did my best. So yeah, I think that's about it for this video. A few terms I'd like you to maybe recall on or learn more of are a neural network, right? And that it is a connected layer of neurons. I'd like you to focus on what a neuron is. It's a mathematical function. What a fully connected neural network, what activation functions are, and the ton functions. So that's what we covered in this specific video. I was talking a lot, and hope in the future videos when we're coding, I won't have to talk too much and let you guys focus. But I hope I gave a pretty good understanding to you guys of how neural networks work, what are they, and so you can get started on your course to machine learning neural networks with TensorFlow, and we might use Google Colab in the future. So thank you guys for watching, and what I do recommend is to watch one of these videos each day in this course. So that maybe helps you. You don't have to have all this information at once. But anyways, thanks for watching this specific video, and see you in the next one. Alright guys, so in this part, I want to just get set up with our environment so we can use this environment to start coding for the rest of this video. So we're going to be using an app coded by Google called Google Colab. So how this works is you have your computer, we can say, is this small square, and this would be Google's big machine, right? And what's happening is when you log on, Google's connecting your machine with their machine. All right, so now this machine already has all the libraries and modules installed. So what's happening is when you write your code, so let's say this circle thing is your code, it's just sending this code and running it on this machine. And then it runs it on this machine right here, and it gives you the output back. So that's it. It's pretty simple, but it's really easy to use. So how we get on Google Colab is we just type Google Colab in our browser, and we click on the first one. So collab.research.google.com. So this works as long as you have a Google account. And what's really cool is it also connects to your drive. So if you want to see any of these files, it already puts it on the cloud. So it's saved for very nicely. So you can see it should open up a file, right? That's called coding collab notebooks, right? And these will be all your notebooks. So automatically adds. So now the first thing you want to do is create a new notebook. And like I said, you want to connect the machine, so you can just click this connect right here. So that's about it, just to get started. Though you do need to import modules, which we'll get started in the next video. So thanks for watching. I know it was a short one. The next one will be much longer. Guys, so last video we created our first notebook in Google Colab, and in this video we're going to be creating our first TensorFlow project. So it's going to be really exciting, and let's just get into it. So in Google Colab we have to import TensorFlow in a slightly different way, just an extra line of code. So how we do this is we put a %, and this is to initialize what version we want, because Google Colab has all the versions of TensorFlow installed on their machine. So you just say %, TensorFlow, I think it's version 2, like that. Let me see. No, it's version, TensorFlow version, and then you can put 2v, I think, that's it. 2x, all right, 2.x. So this is just saying what version it is. Now we can import it regularly by saying import TensorFlow as TF. And there are two more modules that we need to, or one more module that we need to install. Though before we get to that, we need to, I want to, or it'll be easier to import a part of TensorFlow that we call keras. So this would be from TensorFlow import keras. So this allows us to make our project so much easier. We don't have to worry about it'll just limit our amount of code, so we can focus on actually training our model. Actually focusing on the project. So the next module we need to install is matplotlib. So this allows us to graph our images, because we're going to work with a data set where we are going to get an image and show it. So import matplotlib. Dot pyplot. So that's it for importing. Yeah, ASP.plt. So now we can get started with the code. So the first thing that we want to do is we want to get the data set. So this is a data set that TensorFlow, I think, created, and we're just going to use it for now before we actually create our own data sets. So how we do this is we can say keras.dataset dot then the data set. So we're going to work with the data set called fraction mnist. All right, that should be it. So we can just store this in a variable called data. All right, now what we want to do is we want to basically store all the data from this data set. So we need to store it in things called training images and testing images. So training images are the images that we use, or the images that we use to actually train our model. But the testing images are the images that we use to just test them out. So we're just testing it, the neural network. So yeah. So we can split this into training images and testing images. So train image and train labels. I think I forgot to explain what labels and images are in the last video. So I will do that in the next tutorial. So because I think that'll relate a little bit more to that's a test label. Right. And then we can just say equals our data, and we want to load all this data into this. So only because we have keras, or we're using keras, we can do this. Right? Now what we want to do is we want to show the image. So we can just say plt, so our matplotlib.pyplot.im show. And then this is a list. So we have to say train image, and then what image. So this is what image in the list. So there's only 10 images in this data set. So we can type any number from 1 to 10, or 0 to 9 actually. So I'm just gonna go with 7 because I think that's a nice number. And now we just need to show this image. So plt.show, just like this, and this should work. Right, something went wrong. Keras is not defined. Oh, what happened with that? Did we spell it wrong? Actually, I know that happened. I think we need to run this first. All right, now we can run this. So we still get an error. NumPy ND array is not callable. Oh, this is the reason. It's a list, so we need these brackets. All right, sorry guys for that. So you can see it shows this image. So it is a fashion MNIST. So basically, when we actually pull up this this documentation, so it has any of these images. So class names, it can be t-shirt, top, trouser, pullover, dress, coat. So what we got is 1, 2, 3, 4, 5, 6, 7. So we got this shirt. So actually it's 0, 1, 2, 3, 4, 5, 6, 7. Wait, no. 0, 1, 2, 3, 4, 5, 6, 7. That does not look like a sneaker to me. I guess it's just a shirt. I think it starts from 1 in this data set for some reason. Anyway, so we can, let's say we want our ankle boot, we put a 9 here. And this is supposed to be our ankle boot. And if we want a t-shirt / top, we put a 0 here. So that's our shoe. Trouser, wait, what happened? I guess that would be our sneaker. I don't know. I think it's just, I don't know what happened. But yeah, so you can just play around with this, see how it works. One thing I do want to add to this is I kind of want to add an input, so the user, it's kind of like user playable. So we can do this just by saying like what is equal to int input, and inside like pick a number 1 through 9, and then like that. So then we can just replace this 8 with what. Alright, so that's a pretty nice project that we have just coded. So let's say we say like 5, it shows the image for 5. So that would be 1, 2, 3, 4, 5. That would be our code. Alright, so thank you guys for watching this video. I hope to see you guys in the next one. Guys, so in this video we're going to go deeper into what we talked about in the first video. So if you can remember, in the first video we talked about what neural networks are and how they work. We also went deeper into what layers or connections neural networks can have, and things like activation functions. We talked about how every neural network is a mathematical function, and you can think of that you can think of as a value, right? So if we refresh to our diagram that we did before, we kind of had these like circle figures that in a model we could describe as neurons, right? And if we go back, just for a quick refresh, right? These neurons are mathematical functions, right? And basically, what a neural network is layered neurons. And I know I've told you guys this a lot in the first video, but just trying to refresh so you guys don't get confused. But then we also talked about activation functions, and I didn't go really deep into these activation functions. I kind of just told you that, all right, this is activation functions are a thing, and kind of like this is what they do. But it was even when I watched the video over and over again, it kind of like it wasn't a great explanation. So I'd like to recover that in this video. So I will like to inform you that this video does require a pretty good understanding of direct variation. So maybe you guys have already learned about this and you've already kind of understood what I meant in the first video. But if you guys haven't, then I'll just try to explain to you again, right? So basically, direct variation is, in mathematical terms, it would just be a ratio that gives you another value, or the constant of variation, right? So I don't want to get too deep into this because I can make a full course on just what this is, but we're just trying to focus on just the spectrum. I know, like, it does, I mean, this is pretty important and it's not getting off topic, but I mean, I'd rather, like, you don't have to, like, watch a full 7-hour course or something like that, humongous course just to learn this. Just try to scratch the surface on topics that we don't really need to know to code neural networks, but like know about them, so we can focus 100% or 99% on the code. So basically, what I mean by that is two values that give you another value. So a ratio that gives you another value. So, for example, a price, right? So, for example, let's say that you're buying oranges at Ralph's, right? So you have these oranges on the shelf, right? And for each orange, right, let's say it costs 50 cents, right? I mean, I'm not trying to be, this doesn't have to make sense, the price. So let's just say it's 50 cents, right, for each orange. And basically, this would be an example of direct variation because your price is always a constant. What I mean by that is when the amount of oranges you get, so for the amount of oranges you get, the price goes up, right? So that many times. So if you get one orange, the price would be 50 cents, right? I'm going to try to write in actual text. So one orange would equal to 50 cents, right? So equals 50 cents. I don't know how well you guys can see that. It's really small. I try to make it a bit bigger. It's much bigger. So one would be 50 cents, right? Now, if we get two, the price will always keep going up by our constant of variation, which is 50 cents. So if you get two, it would go up by 2 times our constant of variation, so 100 cents. 3 times our constant of variation, 150 cents. So you can see that our constant of variation is this 50 cents. The price, 50 cents. The price never it's never in a it's always 50 cents, right? No matter how many you buy, I mean, obviously discounts and things, but no matter how many you buy, it'll keep going up by 50 cents, right? So let's actually delete all of this. And because it keeps going up by 50 cents, if we were to draw a graph, right, of this, make it black again. If we were to draw a graph, right, and this shows the prices, right? So the x-coordinate would be amount, and the y-coordinate would be the y-coordinate would be the price, right? So basically, let's write some text here. So this right here would be, let me just make this a little bit smaller. This right here would be 1. This would be 2. This would be 3. And this would be 4. And now this would be 50. All right, let's go down. This would be 50 cents. A cent. This would be 100 cents. So basically, it would keep going up. So it's kind of hard for me to draw this diagram-y type of thing here. So I'm trying my best. And I know actually the diagram, it really helps to understand it. So you can see it starts off at this 50 cents right here. Then it keeps increasing by the same amount. So now this would be 100 cents. This would be 150 cents right here. It keeps going higher and higher and farther in a bigger x value, because obviously it is, right? And it keeps going by 50 cents. So it keeps going in the same direction. All right, so this is literally how it looks. And because this graph, it's constantly increasing by a constant value, it's always going in the same direction. So you can see here, this actually forms a line. I mean, obviously in this example, right, it's not a line because you can't have negative produce. But really, in neural networks, a mathematical function can be negative as well, right? So you can have -1. So this is actually forming, I mean, here it's a ray, but really, in an actual neural network, it would form a line, right? And if we look back, this actually looks like our linear regression function that we talked about before. See, this is literally how I drew it, right? And this looks exactly the same, and that is totally correct. Both of these are linear regression functions. So what that's saying is that what a linear regression function is showing is it's showing that all the values are going up by a constant of variation. So they could be going up by 1, it could be going down by -1. So really, it's forming this line. And that's not complexity, right? I mean, in computer, that's not complexity, because it's going in the same order every single time, right? So in your brain, right, I don't want to get too deep into this either, but like, for example, when you're brushing your teeth every single day, your brain makes that sequence automative. It makes it automated because it's the exact same thing over and over and over again. You probably brush your teeth thousands of times. And now your brain isn't really worrying about that. So it automates these things that keep happening over and over and over again in the same sequence. So basically what your brain is doing is it's just automating brushing the teeth. So really, you're brushing your teeth in the same exact way every day, but you don't think about it because it's automating it, and that makes your brain so it doesn't have to focus on brushing your teeth. So it can do other things that are more complex, right? Complex again, right? That are not in this same pattern, right? So that's how your brain can accomplish so many things. So now when we go back to our activation functions, right, we see that we have something that looks like this. I just want to try to draw this the best I can. I mean, it's not the most straight lines, but again, I'm using my mouse to do this. It's not some drawing pad. Basically, this is how something that is not a direct variation will look like. It could be somewhere here, then it could be here, then it could be here. And you can see all these loops and things. It's not really going in a straight line, right? It's kind of like here and here. And it's all different values. It's not always increasing by 1 or always increasing by a constant of variation. It's getting from here to here to here to here. So when we draw this line, it's going to be kind of hard, right, for me to draw it here. But instead of these points, just think of them as curves. So you can see we see all these different curves. And this is what I mean by complexity. It's not automative, if we're talking about the brain, right? This would be something like a test, right? This might be something like a test. I mean, I'm not an expert on this. I'm just, trying to give you some usual examples that are common examples that we might do, right? But just don't go too hard on this neurology or the biology. Just try to understand the concept, right? On a test, all the answers are different, and your brain is experiencing problems and challenges. So it has to solve these problems with full focus, right? It can't automate these problems because it's never experienced these before, hundreds of thousands of times. So these problems, they would be complex because your brain hasn't experienced it yet. It's trying to figure it out. So I hope you kind of understood what I mean with the activation functions and how they help. So basically, they allow you to go in very different values without even without having to have to go by the constant of variation, right? So you can have so many different possibilities in this spectrum, rather than in a linear regression function. The only possibilities it can be are multiples of 50 cents, right? In our example. So the only possibilities for the price can be 50, 100, 150, 200, 250, 300, 350, etc. cents. Here, the prices can go from, it can be 1, 3, 5, 6, 9, 100, 2 million, 5, right? So it can be all these different prices rather than just multiples of 50. All right? So I'm not trying to say that like it's wrong that this is how it works. I hope you don't interpret it this way. I'm not saying anything is wrong. I mean, I'm just saying that how activation functions increase complexity. All right. So I know we talked about the ton function in the first video, and that graphs anything from 1 to -1, by the way. So instead of being in a specific order, adding by the constant of variation, this can be infinity numbers between 1 and -1. Right? Now, if we keep increasing these distances, you can see that it's it's much more, right? So if we have a 9 to negative 9, it would be, you can graph it in all these different values rather than just graphing by the constant of variation, right? So, I mean, I hope you understood it. I mean, I tried to make it my my best, but I know if you guys haven't really discussed about these things, it might be hard. Yeah, I did my best, so I hope you guys got a better understanding of how this works. If you didn't, you can just maybe like put a comment down below or like contact me if you have any questions, and I'll try to make a video with all the questions. Guys, and in this section we're going to be doing something really cool. So what we're going to do is we're going to create our first actual neural network model, and what this model is going to do is previously in the 2 videos back, right, what we did was we created a project that loaded images and showed the images. Now we're going to be adding to that project. So if you haven't gone through that project yet, you need to go through that before you get into this video. We're going to be adding to that. So basically what the neural network is going to do is it's going to try to figure out what the image is by itself, right? And we're going to be training this model we're going to be training this model so it can be its best, right? So right now I just want to show you guys basically how our model is going to look in the end. All right. So if you guys remember 2 videos back, all the images were shown in 28 by 28 pixels, right? And I don't remember if we tested it out, but basically what this means is that there is a list, right? So just think of these boxes as like brackets. So this is a list, and there is 28 lists. So you can just say like x28. And basically, there were lists inside each list that contained a value. So this would be 1. Right? And then it would keep going. So after, like, it would end up at 28. So here we can draw 28. It's kind of hard to see with these diagrams. So remember, I do have the notes and everything, which has the diagram written. All right, so basically what this is saying is there is a list inside of a big list, and each list inside of that big list is a value, right? And we have 28 of those lists. So if we do the math, 28 times 28 is 784, right? And we do not want to give all these different lists into one neuron, right? So what we need to do is we need to change our model in a way that we can give it as one list, right? And we do this by flattening out the list, which means we take all 28 lists, we smush them together where it goes in a pattern like this. Instead of all the brackets, I should have drawn it like this, right? So this is how it used to be. 1, and then like 2, and then all the way till 28, and then this list 28 times. Now what we're doing is we're flattening it out so we have 784 values in one list. So 1, 3, 4, ... so we get to 784. Right, so this is much easier to feed to one neuron. All right, So now our model is going to look something like this. Our input layer will have 784 neurons, right? We just talked about that. So we can just say 784 here. And our output layer should have our 10 neurons. Because remember, in our data set, there were 10 different labels. We talked about that in the previous video. So 6, 7, so 0 through 9, 8. I'm just going to draw them here, 9 and 10. All right, and basically we are going to have hidden layers as well. Right, and these hidden layers will just help with the complexity. All right, I know I'm not drawing the best diagrams and things, but I hope you kind of understand it, how this is going to work. All right. So, basically, that's what we're going to be doing. So 9 or 10 neurons in our output layer, and each of these neurons, by the way, is going to be the percent of how much it thinks is the actual image. So what I mean by that is, let's say this would be pants, right? P for pants. Now the value of this neuron, if the image was some shirt, it would be something like 0.5 or something like that. Then or 0.05 actually. And then let's say this one was our shirt, it'll probably have a like 75 or something like that. Right? As we train, it'll go higher and higher. But I mean, I'm trying to explain it the best I can. So I'm just saying that the value, each neuron holds a specific image or label, and the value, the mathematical function, would be the percentage it thinks that the image is its neuron or its label. All right, so I know my diagrams weren't the best today. I tried my best, so that's why you can just look at the notes down below and you can just look at the diagram better. But now let's actually get into the code, right? I think that'll put us on the roll. All right, so we can just go, if you guys remember, to Google Cloud, where we had our notebooks and things. And basically, we can actually just edit on our data fashion MNIST project. At least that's what I called mine. And you can see that I have already finished all the code. Okay, so basically all this code, I'd rather you not write it all out right now. I'd rather you kind of just listen to it. Don't type it all out. And I will give you this notebook so you can just copy and paste it, all right? Because these are some complex things, and I'd rather not you write it all down, because when I did this, I had a lot of errors and things till I actually got the right thing. So just listen for now, see what's happening, and then you can just copy and paste the code. But please do not just copy and paste the code. Please try to understand what I'm saying. So the first thing that we need to do when we are creating our model, right, is we need to define the layers in the model. All right, so really we only have 3 steps here: defining the layers of the model, training the model, and defining the layers of the model, compiling the model, and training the model. All right, so our first layer, or our first step, we need to define what layers we have in our model, and we just discussed that on our diagram. So basically, we said that we will have our input layer, and this will have 28 by 28 values, or 784, right? Then our next layer would be our hidden layer, and I actually didn't talk about that. kind of forgot. So our hidden layer, we would have 128. All right, rather not go back to drawing diagrams. So basically, we're just gonna have 128 neurons in our hidden layer. All right, and you can see this activation function. We're using the ReLU. I don't know the longer term for this. When I find it out, I'll tell you in the comments. All right. And our last layer is our output layer, and this has 10 different values. And we're using the softmax activation function. All right. So that's how we create our model. Now what we want to do is we want to compile this model. So we want to basically add some tweaks, and we want to add, not tweaks, but we want to add the information about this model. All right. So our optimizer is Adam. You guys don't need to worry about this right now. Just follow along. And our loss is sparse categorical cross-entropy. And basically, you guys don't need to worry about this either. And then our metrics is just saying that we want to focus on accuracy. So don't worry about this. Just know that we're just compiling our model here. Finally, let's train it. So we are going to train with our training images and training labels. And this is very important, epochs. So basically what epochs means is how many times we're going to view the image. All right. And this sometimes confuses the model, but it also can help the model's accuracy, because if it's seeing an image over and over again, it can kind of like basically it can test its theory out 5 times or this many times, right? So that might increase its accuracy as it sees, okay, maybe this I'm 70%. Then the next time it sees the exact same thing, so now it's 80. Then it sees again 90, and then it sees it again 95. It sees it again 99.9. So basically, this allows us to train our model or improve the accuracy. Though sometimes it can confuse our model. If it sees different things every single time, the accuracy may go even lower, actually. All right, but we can just put it here because we want our model to be as accurate as it can. If this doesn't work and the model's accuracy is very low, then we can just change it, right? We can change the amount of epochs. All right, so now let's run this, right? This is actually all the code we need, and let's run this. So pick a number between 1 to 9, and these are just the images. So we can choose 5, right? And it shows the image for 5. So you can see it's kind of like a sweatshirt type of thing. And it's taking some time because it's running through all these epochs. You can see number 1, it found an accuracy. So now we can see right here, our epochs are actually working very good. So our first try when we saw the image is we thought accuracy, whatever the actual label was, it thought its accuracy was 68%, right? Then the next time it was 70%. And you can see it keeps gradually increasing, and that's great, right? If we had 1 epoch, right? I mean, the project will run quicker. And once it's done, you can see it only has a 68% accuracy. And last time it has a 77. So now if we train this model again with 5 epochs, it should actually increase its accuracy from 77 because we keep training it, right? So our 5th epoch is what counts. See right here, this is 79. Now we're going into the 80s. Right, so the more we run this program, you can see how the neural network is gradually increasing on its understanding or of these images, what it thinks about them. So now we're at 81. We're up literally 4%, right? I mean, it seems low, but really, if we keep running this will only gradually increase. All right, so what did I just do? Control ZN, by the way, is how you get your thing back. So Control ZN to come back. What just happened? Sorry, guys. Control MZ. Oh yeah, what just happened? All right, perfect. I didn't actually delete it. All right, so that's it for this video. I hope you enjoyed it. And I will put this code on my website. So I haven't added that section yet, but I'm looking forward to adding it. And I'll put all the links in the description. So thank you guys for watching this video. And in later videos, we'll train this model even better, add some things to it that'll help it become a greater model. All right, so see you in the next one. Hey guys, and in this video, we're going to actually use our model to create predictions. So you can see I just ran it, and its prediction is Chaucer, its accuracy is 81%, and the actual image is Chaucer. So you can see this is our expected output. So now, this is a lot of code. Well, it's not a lot of code, but it's kind of some complicated code. So instead of both of us writing it out at once, just like last video, I want to actually just tell you what the code means, and you can just copy and paste it back, right? So I know it's kind of a long thing to write out. So I'd rather I just tell to you what all the code means so you can understand what the code is. And then you can just copy and paste it, because some of these words are pretty big, such as this and this. So, and it has a lot of lists and parentheses, and I don't want you guys to spend an hour just trying to debug your code. All right, so basically, what we want to do is when we are predicting something in TensorFlow, we have to use this model.predict function. So this first line of code is it's just predicting what the image is, right? And it's getting its value in this pre-variable. So this line is just actually predicting what the image actually is. Now, this line, it's just kind of like some formatting. So it's just saying that it doesn't want the grid on the image, so you don't need to worry about that. And this line of code, I know we didn't have this extra part there. So we had this, but we didn't have this CMap thing. So the CMap thing is it's just converting it into black and white. So I think this just looks cooler. You can just delete this if you don't like it. This code is actually saying what the actual image is, right? So you can see down here we have our actual image. So how we did this, how we got this, an X label is the bottom label, so you can see it's below the image. And what it's saying is it's saying the test labels, it's going through the test labels, and it's finding the test labels, the test label whose value is whatever you entered. All right. So that's how we get our actual image, and then we pass it through our class names to get a string value. Then here is this line of code is actually just evaluating what our accuracy is. So you can see model.evaluate, and that's how we get some evaluations with the accuracy. Here is a pretty big line of code, and this is just a title, plt.title. And it's first saying that our prediction is this same code up here. Actually, no, it's not the same code, sorry. So what it's saying is the predictions and passing through data, so the value of whatever you enter. So we enter 3. So 3 is the image that it's trying to figure out what it is. And then np.argmax is numpy.argmax, and what that's doing is it's just lowering the list because this is a list. As I said earlier, the images are 28 by 28 lists. Then here we're just passing it through class names so we can get a string value. Then here, to get our accuracy, we can just say accuracy and then plus. We already found our accuracy here, so we can just add that back. And this accuracy would be a integer, so that's why we have to convert it to string. I was talking pretty quickly, so I know. So just the main parts that you need to focus on is that to this, which is we are getting the value of whatever we entered label. So this is just getting the label, right? And then this is how you evaluate by saying model.evaluate, and this is how you predict, right? So hope you understood that part. And we get our code here. I know I was talking really fast, so I mean, even if I were to talk slower, I kind of like it. I mean, if it doesn't make sense to you guys, you can just contact me again, right? And if you have any questions, just put them in the comments. If you have any questions. So this is pretty quick, but basically, I hope you understood that. And thank you guys for watching this course. It was pretty long. I think it's like an hour and a half, something like that. And I hope you learned a lot. See you in the next one.